Welcome to the short video presentation of our paper GuideCopter, a precise drone-based guidance interface for blind or visually impaired people. Our idea was to research how well a drone-based system is suited for fine-grained guidance of blind or visually impaired people in an unknown or changing environment. Just think about you are standing in an open-air food market and want to grab a peach from the stand. We first started with a concept and related work study that we can't present here due to time restrictions. Please be referred to our paper where you can find the detailed analysis. We compared our idea to current state-of-the-art solutions and identified the benefits a drone-based guiding system offers for blind or visually impaired people. The following phase 1 was focusing on finding the optimal tethering point on the hand. In addition, we researched the minimal forces needed to be perceivable by people in any direction. The evaluation was done in a focus group with blind and visually impaired people. Based on Phase 1, we evaluated in Phase 2 the guiding cues and safety aspects of DroneCopter to ensure a reliable and smooth user experience during the user study. We selected and customized the chosen drone and implemented a framework for data collection for later analysis. Finally, we performed a comparative user study in Phase 3 to evaluate the performance and the user experience when GuideCopter is compared to a state-of-the-art audio guiding system. Due to the limited amount of time, we focus on results of Phase 2 and Phase 3 in the presentation of GuideCopter. To compare state-of-the-art audio cues as shown on the left side to the haptic forces of GuideCopter as shown on the right side, we projected the audio cues to directed forces applied via the drone to the pointing finger of the user. We see the advantage by design of GuideCopter to directly project guiding forces to the user's hand compared to an audio-based interface where the user has to translate the audio cues to motoric movements of the hand. This translation takes time to learn and is individual per person. Our study setup consisted of a customized drone, different objects on a table and the user to be guided. We used an OptiTrack environment to record user movements, the drone and the objects in 3D space. We controlled the drone with a Wizard of Oz algorithm, and guided the user from the starting point to the target. The tabletop view on the left side, and the front-to-back view on the right side highlight the different paths taken by drone and audio guidance. Both sketches together present an exemplarily tracked GuideCopter and audio-guided path in 3D. Before we get to the results, we present an animation that shows the dynamic of the drone guidance system. The task is to begin at the starting point and to grab the pen. It highlights the dynamic to position the hand above the pen, and to signal that the target is reached. Summing up the user study results, the left side shows the mean task completion time, the right side the root mean square path deviation between guided and actually taken path. The task difficulty is defined as the distance between the starting point and the target object size, and its 3D location in the tabletop space. An easy task was to grab a water bottle that is 30 centimeters away in direct line. A hard task was to grab a USB drive on top of books, 145 centimeters away with 2 obstacles in the direct path. The time comparison shows that with raising task difficulty, the speed of the drone guidance becomes a distinguishing factor. Path deviation is close to 40% better with GuideCopter. Explainable drops in tasks 4 and 6 are due to a more linear path characteristic. In task 10, a small target item was placed on top of a larger one, resulting in a reduced circling and searching with the hand when audio guidance was used. Highlighting our results, we see that GuideCopter is significantly faster, has a significantly lower root mean square error and deviation, and a significantly higher system usability scale score, compared to an audio cue-based guiding system that is considered to be state-of-the-art. Interviewing the study participants, they mostly liked the immediate user experience perceived when using GuideCopter. They specifically favored the direct, haptic, and graspable interaction with GuideCopter over the audio cue-based system. With GuideCopter, we hope to lay the foundation for tethered human-drone interfaces to support blind and visually impaired people towards precise user guidance and assistance in locomotion, search, and haptic space tasks in both real and virtual environments. Well, that was pretty much for a 5-minute talk. We hope you enjoyed it and are happy to answer your questions.